pero les quiero agradecer por toda la paciencia que siempre nos tienen y por la buena onda que le ponen a la eco. Así que nada, antes que... ¿Para qué seguir hablando si ellos tienen más que hablar que yo? Así que, Juano, Tai.
Bueno, gracias. Estamos presentando casi lo mismo que el año pasado, pero no es aburrido eso, sino que la parte sorprendente es que se pueda hacer algo parecido a lo del año pasado de nuevo. Eso es lo interesante. Y vino Tai, se le costó bastante. Entonces, en general, el impacto de lo que vamos a presentar, el resultado, uno de los resultados es igual, que podemos leer cookies encriptadas con HTTPS. Pero eso es solo una cosa en realidad, porque con algunas de las ideas nuevas y tanto la misma vulnerabilidad puede aparecer en otros lugares y las mismas ideas para explotarla también. Entonces, el desencriptar cookies es lo primero que se nos ocurrió hacer, que muestra claramente cuál es el riesgo de esto, pero tal vez se pueden hacer más cosas porque es un poco más general que lo de BIST. Entonces, el escenario es el mismo. Es un ataque cuando estás compartiendo la red con alguien. Bueno, siempre estás compartiendo la red con alguien. Es decir, el atacante tiene que poder ver tu tráfico de red. Pero eso no es... Hay gente que le decís eso y ya dice, ah, bueno, entonces no es tan peligroso. Pero cada vez es más fácil eso, o cada vez hay más posibilidades de que un atacante pueda hacer este tipo de ataques. Ahí hay algunos ejemplos. Porque, no sé, yo pienso siempre que me conecto a una red en un café o en un hotel, o acá mismo, que existe esa posibilidad de ese tipo de ataques. No solamente que me pueden usar un exploit contra el browser y instalar algo, sino que estas cosas pueden pasar. Entonces eso es así, es el mismo escenario. Además de eso, hace falta, como con BIST, que el navegador, en este caso, ¿no? en esta implementación del ataque contra los navegadores, contra HTTPS y para leer las cookies, necesitamos, como BIST, iniciar pedidos en el navegador. Que eso es fácil también. Si hay alguien que está en la red y puede leer los paquetes y modificarlos, es muy fácil, porque no todas las conexiones están encriptadas. Cuando usamos HTTPS es para evitar ese tipo de cosas, para que nadie pueda ver lo que estamos haciendo, modificarlo y para saber con quién nos estamos conectando. Sí, que realmente nos conectamos con quien queremos, pero cuando usamos internet todos los días, lamentablemente no son todas las conexiones así. Entonces, cualquier conexión que hagamos que no sea segura, permite inyectar algo ahí, HTML, para poder lograr que el navegador después genere los pedidos que nosotros queremos. Si fueran todas las conexiones encriptadas en el futuro y a todo lugar que entramos es con HTTPS, y ya no se puede modificar el tráfico para inyectar cosas, igual tenemos siempre la opción de hacer que la persona visite un sitio que nosotros controlamos, o nosotros entramos a un sitio que la persona visita, nosotros, digo el atacante, ¿no? Que no somos nosotros, y poner algo ahí. Es casi HTML lo que hace falta. Nosotros usamos un script, pero para hacerlo más rápido, con HTML solo se podría hacer. Entonces más o menos esta es la idea. Cuando estás conectado a un sitio seguro, que al atacante le interesa acceder con tus credenciales, y al mismo tiempo accedes a otro que no es seguro, y se puede modificar el HTML, el contenido de ese sitio, ahí ya empieza, ya se puede empezar. Si no se pudiera hacer esto, la otra opción es hacerlo visitar un sitio. Ese código, porque al final a veces siempre alguien pregunta si esa máquina está infectada, si ya tiene algo ahí. ¿Por qué? ¿Cómo es que esa máquina, ese navegador empieza a hacer pedidos, los pedidos que nosotros queremos, al otro sitio? Pero el código ese es como cualquier página que tiene un poco de código y no es que está solo adentro del navegador, y eso es suficiente. Pero esto la mayoría de ustedes ya lo saben. Entonces, lo nuevo es que nosotros, para poder lograr esto, usamos la compresión. ahí está el problema, cuando se mezcla la compresión con la encripción. Lo de BIST era un problema particular de las primeras, bueno, de la versión de TLS o SSL, que es lo mismo que HTTPS casi, algo muy particular de ese protocolo. En este caso es un poco más general, bastante más general. Siempre que se use compresión y encripción, podría hacerse algo como esto. Entonces, Tai va a explicar en más detalle cómo se hace y los detalles de los algoritmos y todo para lograrlo. Pero tenemos que empezar a ver un poco de cómo es la compresión para entender. Cuando la compresión más común que se usa en todos lados es esta, que se llama deflate, que está implementada hasta en el zip, es muy parecida, casi la misma. Y funciona haciendo dos cosas, que le voy a decir después. Primero, ¿dónde hay compresión? Bueno, como dije, en TLS, que es opcional. TLS permite comprimir. Por muchos años creo que nadie lo hacía, pero Chrome, el navegador Chrome, las librerías de SSL lo permiten, TLS es lo mismo que SSL, pero no todas están configuradas para usarlo, pero casi todas lo permiten. Y hay navegadores que también lo hacen, siempre, como Chrome hasta la última versión, anteúltima. Después está este protocolo Speedy, que es un protocolo nuevo que creo que sí, desarrolla principalmente Google, que es para reemplazar HTTP, para hacerlo más rápido, y comprime siempre, porque es uno de los objetivos. Y después tenemos, cuando accedemos a un sitio, más allá de que SSL tenga compresión o no, muchos sitios comprimen todo el contenido que envían, y los HTML principalmente, y ahí se podría hacer algo similar. No exactamente las cookies, porque cuando usan compresión de esa manera se comprime el contenido, pero no los headers donde están las cookies. Pero hay cosas que se pueden hacer, que vamos a ver después. Y después otros protocolos que usan encripción y compresión, que no miramos en mucho detalle, pero potencialmente se podría hacer algo. Nosotros los ejemplos que tenemos son para Speedy y TLS. Entonces, este algoritmo es compresión sin pérdida, ¿no? Como la música, las películas, las imágenes se comprimen con pérdida, se pierde información pero que no es muy relevante. Estos algoritmos no. Y lo que hacen es, funciona con dos algoritmos, uno que es LZ77 y Huffman. Y siempre van combinados. El primero es este que se llama lempel-zip, que lo que hace es buscar repeticiones de bytes. En todos los ejemplos que vamos a dar son cadenas de texto, pero podría ser cualquier cosa. Que tengan un tamaño mínimo, porque si no, no tiene mucho sentido. Y la segunda vez que aparece el mismo texto, en lugar de repetir ese texto, se pone una referencia a la última vez que apareció. Se reemplaza el texto con dos códigos, uno de la distancia y la longitud, cuántos bytes atrás tiene que ir y cuánto tiene que copiar, y copia eso. La idea es que ese código de distancia y longitud ocupe menos en bits que repetir de nuevo la cadena. Eso de cuánto atrás va es un parámetro del algoritmo. Cuánto byte atrás va a buscar repeticiones. Porque tiene que ver con el uso de memoria y otras cosas. En muchas descripciones este algoritmo habla de un diccionario, que en realidad es medio confuso de que lo llamen diccionario. Es más fácil entenderlo con una distancia y una longitud que se pone ahí para reemplazar el texto. Y la otra parte del algoritmo es la que, cuando aparecen nuevas letras, nuevos bytes que no aparecían antes, que no se pueden hacer una referencia a una aparición anterior, que hay que ponerlos literalmente, se usa este modo de codificar los bytes en menos bits. Cuanto más se repite un byte, se hace un código que ocupe menos bits. No necesitamos entender en mucho detalle cómo se hace eso, pero esa es la idea. Si se repite poco, va a ocupar más bits; si se repite menos, lo mismo que poco; si se repite más, ocupa menos bits. Y también es importante saber que no hay que demarcar el límite entre cada código, porque ningún código empieza de la misma forma que otro código, entonces no es necesario poner límites y es muy óptimo para comprimir. La librería, esta cosa de todo el mundo para comprimir, que es zlib, tiene dos modos, dos tablas de estos códigos. O sea, cuando uno termina de comprimir, tiene como resultado una tabla que para transformar esos códigos de bits a los bytes originales. Son códigos de pocos bits. Hay una que viene fija en la librería que sirve para comprimir bien algunas cosas como inglés y se usa. No tiene mucho sentido que se usa, pero se usa. Y después hay otra que se va generando de acuerdo a la frecuencia de cada tipo de datos en particular. La tabla esa que es fija, los códigos son más largos que si en general, digamos. ¿Por qué? Porque cuando haces la tabla para unos datos específicos, tiene menos códigos y entonces pueden hacer que haya códigos más cortos. Cuando las tablas tienen más códigos, ya no se pueden usar los tan cortos. El ejemplo más obvio, si tenés dos códigos, 2 bytes que querés comprimir, puedes usar el 1 y el 0. Cuando tenés más ya no puedes usar eso, entonces ya no puedes usar códigos de un bit. Eso, saber que esa tabla fija en general tiene códigos más largos, es importante también. Entonces, lo que básicamente hacemos es hacer que, en este caso el navegador, o una parte de las dos que están conectadas, genere mensajes que comprime y luego los encripta, que tengan algo que nosotros controlamos. Por ahora que controlamos. Tal vez se podría hacer sin controlarlo, pero sabiendo qué es. Entonces tenemos algo que el atacante controla y un secreto. Todo eso se junta y se comprime. Y después se encripta. Entonces la idea es que nosotros podemos ver cuánto se comprimió. No podemos ver los datos, pero podemos saber el tamaño de los datos después de comprimirlos. Y como controlamos parte de la entrada, podemos saber si se comprime más o menos cuando cambiamos la entrada. Como la compresión se basa en eliminar las repeticiones, la redundancia, si se comprime más, quiere decir que en nuestros datos y en los originales hay más cosas en común. Si se comprime menos, que hay menos cosas en común. Esa es la idea básica. Cambiar los datos, ver si se comprimen más o menos y así ir adivinando cosas de la otra parte del mensaje que no conocemos. En el caso de HTTP y los navegadores son las cookies. Ahora, ¿cómo podemos ver esta longitud? Es muy fácil. En SSL y TLS no hay ninguna intención. En la práctica no la ocultan. Está por acá, se ve, más o menos, que la longitud de los datos está ahí es un número que podemos leer de la red y es preciso en bytes cuánto ocupan los datos que se están transfiriendo. Eso nos permite hacer esto. Entonces, este es el ejemplo concreto con HTTP. Igual que con bits, hacemos que ese código que nosotros tenemos en el navegador, que por ejemplo en el navegador tenés un sitio seguro, tu mail, el banco o algo así, y cualquier otro, donde nosotros logramos poner algo de HTML que controlamos. Y hacemos que este sitio haga referencia a archivos en el otro sitio, en el seguro, que no tienen por qué existir. Lo único que queremos es que salgan los pedidos del navegador, que se compriman y se encripten y salgan. Se puede hacer con imágenes, poner una imagen, decir acá agregás una imagen en tu página que apunta a https://gmail.com/ algo, y ahí el navegador va a tratar de ir a buscar ese archivo, aunque venga de otra página, y comprime y encripta y lo envía y nosotros después lo vemos en la red. Acá no se nota la diferencia de colores, pero la idea es que cuando lo que nosotros podemos controlar es la parte de ahí arriba, que es el nombre del archivo. Todo lo demás lo agrega el navegador. Muchas de esas cosas las conocemos, como la versión del navegador, a qué sitio se está conectando. Las otras son las que queremos adivinar, el contenido de la cookie que necesitamos para acceder al sitio. Vamos a ver una diferencia cuando entre el nombre que nosotros estamos pidiendo, el nombre del archivo que nosotros estamos pidiendo, y los datos de la cookie haya algo en común, vamos a ver una diferencia en el tamaño de los paquetes que se envían. Eso es básicamente toda la idea. Acá está en un gráfico, ¿no? El atacante sigue en contacto con el navegador. Acá esto se lo pueden imaginar como dos tabs que tiene abierto, aunque uno lo puede estar cerrado, pero lo que necesitamos es que estén las cookies todavía. Y va tratando de adivinar letra por letra, a veces lo podemos hacer mejor que letra por letra, y hace que se generen pedidos y vemos la longitud. Es eso. Con bits era muy parecido, pero no veíamos la longitud, sino que buscábamos otras cosas. Entonces lo que primero vamos a ver es una demo de esto funcionando y después Tai va a explicar todos los detalles. ¿Demo? We have now.
continue and then...
Bueno, estos son los resultados más o menos que obtuvimos en la práctica. ¿Cuántos los navegadores que eran vulnerables eran Chrome porque usa compresión, sí, trataba de usar compresión siempre, y Firefox porque usa Speedy, porque la compresión no la usaba siempre. Y servers con Speedy no hay muchos, porque es algo nuevo, pero hay una tendencia a usarlo, y tal vez es el próximo HTTP. En particular estos dos, Gmail y Twitter usan. Y después, la compresión en SSL es más común en los servers, porque nosotros necesitamos que tanto el cliente como el server tengan compresión. Según alguien que escaneó internet buscando cuántos servers usaban compresión, es el 40%, y probamos con sitios como Dropbox, GitHub y algunos más, algunos de tarjeta de crédito, y funcionaba, pero les avisamos y ya lo arreglaron. Igual hay muchos más todavía. Tenemos que buscar ahora alguno para la demo, porque eso ya no sirve. Y la idea esta de hacer esto en realidad existe hace tiempo. Incluso en uno de los RFC sobre estos protocolos dice, ojo, hay uno, el de TLS dice que el atacante puede ver, que alguien en la red puede ver la longitud y dice, tené cuidado con eso. Y hay otro que habla de cómo implementar la compresión que dice, tal vez cuando alguien implementa la compresión, en la longitud se puede saber más de lo que se sabía antes sin compresión. Pero lo que hicimos nosotros es hacerlo práctico. Un caso muy práctico es las cookies de los navegadores. Porque HTTP te permite hacer este tipo de ataques donde vos tenés que controlar parte de los datos que se encriptan muy fácil. Pero es posible que se puedan hacer más cosas. Y lo del año pasado funcionaba con un tipo de algoritmos de encripción. Y la recomendación era pasarse a otros que funcionan distinto para que no sea posible BIST. En este no importa el algoritmo de encripción, porque nos importa la longitud. Y, de hecho, RC4, que era lo recomendado para evitar BIST, es un poco más fácil que AES, porque con RC4 se hace exactamente la longitud en bits de los datos. En AES hay un relleno y no lo hace exacto. Bueno, ¿hasta ahora alguna pregunta? Antes de ir a los detalles de cómo funciona todo. ¿No?
So we will give a recorded demo now, and now if we have enough time at the end of the presentation, we will give a live demo. So this demo I just recorded like last night. Where is it? The demo is against Twitter. Yeah. So maybe we should. Oh. Okay. So if you use the own, like this is the own version of Chrome, because Chrome has upgrade maybe 2 weeks ago, and Firefox also upgrade. So if you use the latest version of Firefox and Chrome, you will be safe. But be careful with your mobile phone, because maybe you haven't upgraded your mobile phone. And Android and Chrome on like Android browser and Chrome on iOS, and Android also support Speedy. So this is the demo against Twitter Speedy implementation. So we will sign in to a throwaway account, and we will show that this is not like connection is not compressed, and this TLS 1.0, and so we switch to the proxy. We use the proxy to make it easier. We can just like using some kind of like transparent proxy and things like that. And when you serve to some like non-HTTPS site, the proxy will inject JavaScript inside the website. I can show the JavaScript. It's just very simple. Yeah, it takes time to run, maybe 3 minutes, so we can spend some time to look at the code. So this is the JavaScript. You can see it just open a new image, create image, create speedy image. I have 2 different versions because I want to save bandwidth. And just basically, okay, the target is twitter.com, and then we just create image, a lot of images to Twitter. So if you don't need JavaScript for that, right, you can use like meta repress or maybe something else just to repress and return a very big static HTML file with a lot of email tag pointing to twitter.com. Let's go back to the video. So if you look carefully, it's maybe difficult to look on the screen, but you look at the end of the screen, you will see some cookies. We derived the cookies, so we found out Twitter is kind of weird that they have two kind of cookie system. One is very long and one is shorter. So we target the shorter one. And the speedy attack is better because you can basically, doesn't need to decrypt everything. You just need to target specific cookie that you want to go after. See, it's finished the first cookie. The first cookie TWID, and the second cookie is out_token. And we will release this video maybe, yeah. And when you look at the video, you will see that the exploit, sometimes it chooses the incorrect bytes, but when it chooses the incorrect bytes, it knows and it's back up to choose something else again. So it takes a little like more time to go forward, choose something like decrypt one by maybe it detects something wrong and it's go backward, but eventually it will get the whole cookies. So when I record this video last night, it took like 3 minutes. And because my one of the problem is my internet connection at the hotel is not very well, but not very good. So it's got the cookie, and I will use the cookie to sign in to Twitter. This is the incognito mode in Chrome. You see that I will copy the cookie from tweet ID, and we will, maybe if we have enough time, we will do a live demo. It's maybe more interesting. Thank you. Okay. You can go check out that account. Okay, so the second part of the presentation will be more technical. Like we will discuss like what kind of problem we got and how we solve it, and we actually at the end of the presentation we will discuss an attack that doesn't require any knowledge of compressions. You can just forget anything that Julio told you. And we will have a very nice attack that works, even if you change the algorithm, it still works. So let's come back to the slide. Where is it? Here. Okay, so last year, I wasn't here, but I was here virtually. And so last year we was working on BIS, and actually BIS has a lot of cool ideas that we reuse in Gram. So actually BIS opened the path to Gram. It has so many ideas that when we look at the idea long enough, the Gram idea will just pop up. And the first idea is BIS so that it's very easy to perform chosen plaintext attack against HTTPS. You should do this. And the second idea, it's very easy to turn the browser into some kind of encryption oracle for you. But you can very easy to ask the browser, okay, encrypt this for me and then send it to me. Basically, that's what we do. We create images pointing to the target server, and the way that the browser does is kind of weird. It concatenates what you send it with some secret and does some transformation together, and then send the data, send the ciphertext or send the packet out the network. That's the first idea of BIS. The second idea is use the URL to decrypt the cookies. URL is something that the attacker controls, and we can easily change it. That's the chosen plain text. But the third idea is the more, I think that's the most important idea. When you look at network protocols, you will see that each layer has different boundary. Like when you move data from the upper layer to the lower layer, and you move the data across protocol layer, protocol boundary, then weird things may happen. And BIS, in BIS, we move the data out of inside the block, like the ciphertext, the cipher block size boundary. And what the new thing in crime is, instead of using crypto vulnerabilities in CBC mode, we just need an info leak in the compressed record length. And then we use two new kind of boundaries. The first boundary is the compressor window size. We will talk about it in a minute. And the second boundary is TOS record size. And when you look at this, you remember this, and then you will see that all of our attack, maybe most, not all, rely on this ability to move things across boundary. And when you apply this technique to all the protocols, I think you may find vulnerability. Because when I try to use the same technique to all the protocols, and I can almost immediately see some problem with it because we can move things across boundary. So Julio told you that's length in the leak, the leak info. But the problem with length is the number of bytes, and display is a very compact format. It's output in bits, it's in an insane file format. If you look at the RFC, you will see that. If you look at the RFC, you will see that it's the double encoding and everything. Yeah, you don't know how to use a Mac. So the length of the request with a match, we need to make sure that we identify the correct guess, right? Because we make a guess, we ask the browser to send a request, so we need to make sure that when this is correct, we know. But if you look at the network level, you will see that the 63-bit request look exactly the same as the 59-bit request because of the padding. You can't differentiate them. So this is one of the main problems, one of the main challenges, and all of the attacks that we develop try to solve this problem. So the first idea, which we call two tries, is we need to record the window size, the role of the window size. So in display, they define a parameter. The name is window size. Is it how far the compressor will go back to look for repetition? When for example, when you see some string like Ekoparty, then how far it will go back in its input stream to look for that string, and the default value is 32 kilobytes. So if the distance from the current string, current input to the previous occurrence is larger than the window size, then it won't be replaced by a distance and length encoding. So window size is essentially a boundary. So the idea here is we move things across it to see what happened. So we have for each guess, the idea we send two requests. That's why we call it two tries. So the first request is with the guess inside the window of the cookie. And the second request is just a permutation of the first request with the guess outside, just outside the window. This is a summary, maybe the next slide. Let's make it better. So this is the oracle. This is the oracle that when you look at the network, you see if your guess is correct or not. If the guess is incorrect, then it's incorrect. So either you move it inside or outside the window, doesn't matter, right? Because it's incorrect, so nothing will be replaced by anything else. But if the guess is correct, then the guess will be replaced by a reference to the cookie in the first request, right? Because it's inside the window and it's a match of something in the cookie. But the guess won't be replaced in the second request because even though it's matched something, it's outside the window, it's outside the boundary. So in the first case, when the guess is incorrect, the length of two requests will be the same. But in the second case, the length will be different. I won't say that the length of the first request will be smaller. It may be different. It may be like larger, it may be smaller, but it will be different. And this is the order. Like when you have a guess, for example, when you want to guess the first byte of the cookie, you send two requests. And for each guess, you send two requests. And basically, cookie is base 64, right? You have 64 characters. And for each character, you send two requests. You look at the length, you compare them. If they equal, you know, oh, your guess is incorrect. If they are different, you know, oh, your guess is correct. And you can by to decrypt the whole cookie. So the pros of this approach is work for on kind of like compressions, like regardless of where you use compression on the transport layer or the application layer or from the server to the client or from the client to the server. We can make it false positive free, like we can have few tricks to make sure that we never decrypt the wrong cookie. But the cons is like it requires linear to, like if you have 64, if the cookie character set is 64, then you have to send like 128 requests, right, to decrypt one byte. And it may fail when the cookie contains repeated string. So this why it fail if it contains repeated string because basically you want to guess the second when it's come to the second part of the cookie that is repeated inside the cookie itself, then that second part has been replaced by the first part already. So your guess won't match anything. That's why it may fail. Yeah, maybe there's some other tricks to make it work. And the third problem, which is basically like, this is why we spend a lot of time on this attack and then we decide, oh, maybe we move on to the next one because it's better, it doesn't require any kind of knowledge of deflate and doesn't require us to read like deflate.c because zlib is basically contains a lot of optimization and it's very hard to create an 8-bit difference if you don't understand how zlib and deflate.c works. So this is the first attack. So the second attack is a variant of this first attack. And in order to, like, the second attack applied for Speedy, but it may apply to all the protocols that does the same thing as Speedy when it comes to compression. So this is a few, like, introduction to Speedy. Like, Speedy is like a new kind of networking protocol for transporting web content. Like, it's similar to HTTP, but like faster, it's really faster. And one of the goals is to improve web security because the people who design Speedy want to make sure that when you use Speedy, you use it Speedy over TLS. So it's basically improve web security. And the third thing is Speedy use compression to reduce the bandwidth. Like the smaller your request, the faster you send it. So Speedy, like instead HTTP, maybe the next slide. Yeah. So I will explain how Speedy use compression in the next slide. But this is some more information about Speedy. Why Speedy is important, right? So IETF has started maybe a process or something to file for HTTP 2.0, and Speedy was selected as the starting point. It's not like they just use Speedy for HTTP 2.0, but it will be a starting point, and they will work on it to improve and And when it's done, I don't know when, but Speedy will replace HTTP 1.1. And for server, we have like Google, Twitter, WordPress, Airfile, Cloudflare. And for software, we like Apache, HTTP, like they have a module for that, and Nginx, and yeah, basically. So there's like this, sorry. And for clients, we have Chrome, Firefox, Opera, maybe something else. We are not sure, but we test Chrome and Firefox. Okay. So how Speedy use compression? So deflays. They use deflate, as we told us. We told you when you see compression on internet protocols, it's deflate because basically there is no one on the algorithm, so you can basically use it without fear someone will sue you someday. And so the nice thing, Speedy use. So you remember HTTP? They also use compression, but they don't compress the headers. And Speedy, one of the selling point of Speedy is they compress the headers to make sure that the headers will be compressed and will be very smaller than HTTP request. The nice thing about Speedy is they use the same compression context for all requests. I will explain this better in the next few slides. But basically, they use the same memory, the same object to compress again and again, instead of like initiate a new object. So why they do that? They do that because it allows them to have better compression. Because basically, when you compress the first request, and if the second request mostly look like exactly the same as the first request, then you can just reduce the size of the second request very small. Because you can just replay everything in the second request to reference to the first request, even though they are two separate requests. So, but like share compression context is very dangerous because at one hand it gives you better compression, but at the other hand, subsequent compressed headers are so small that Zlib decide to use fixed Huffman table, and fixed Huffman table is nice. So recall that we have a slide about Huffman coding, and we said a fixed Huffman table use 7 to 9 bit codes for everything. Why is used? Because basically, I don't know if Julino explains to you guys, but basically because it has to encode everything. So the tree will be longer, and it has to use more bit to encode everything. So it's easier, much easier to have a difference of 8 bits. This is one of the challenges we have to solve. Like we have to make sure that we have a difference of 8 bits. And because now every single code uses 7 to 9 bits, so just a small change, just a new addition of a code, remove of a code, then we have a 8-bit difference. So this is nice, and this is what we just demo, like Speedy and compression. So the algorithm is simple. Like the first thing we do is because we want to reset the compression context. Like we want to override the dictionary. If you guys know how compression works, so deflate, they have a dictionary. When you have new string, you look up the dictionary to see if it has seen anything in the dictionary, and if it has seen it, replay with a back reference. So basically, we reset the compression context to make sure that we know what's inside the dictionary. Because basically, every time you request something, you send 2 requests. The first request will override the dictionary, and the second request may benefit from that. And the second step is we send another request with a wrong guess. The purpose is to get the base length of the wrong guess. Right? How long is the request if it contains an incorrect guess? Then the third step is basically just for each guess we send a request, and we use the base length to spot the possible correct guesses. Like if the length of the request is smaller than the base length, then it's probably correct. We collect it, put it into a bag, and then we try again until the bag contains just one byte, and we know that byte is likely to be correct. So this is the algorithm. Any questions? Okay. So this is basically what I just say. You send the first request, Twitter equal to A, and then this will be compressed to something like this. Like the first one is 100 bytes the distance. Suppose that the home request is 100 bytes, and 10 is the length of get GAT space / TWID equal, which is 10 bytes. It will be reference something else in the last request is in. And then the second request you see is basically the same because the dictionary already contain GET space / TWID equal. So the second request just replace that string with a reference to the string inside its dictionary. And basically everything will be look like this until you hit the correct guess. When you hit the correct guess, nice thing happen. The first thing is GET space / will match the GET space / in the last request. But the correct guess TWID equal to S will match the cookies in the previous request. So it will be replaced. You see the difference. Like instead of 110, it will be split to two code, 105 and then 13 and 6. 13 is the length from here to the cookie. So basically, this is just a very small change, right? Just a few new code, addition and change of some existing code. But I told you because Speedy use fixed Huffman table. No, not Speedy, but Zlib decided to use fixed Huffman table because this is too small. It doesn't make sense to add a dynamic table in front of it because the dynamic table may be very big. And it doesn't make sense to use a dynamic table. So it's want to save space, and one of the techniques to save space is use something that specified in the standard so that you can include in the source code itself. You don't need to build the table. You don't need to store the table. And this small change is enough because basically each like code will be 8 bits. So this will be create like maybe 2 byte difference. And when you look at the network, you see, oh, this is correct, the correct guess. So this is the idea. Any questions? Okay. So the advantage of Speedy is it's still like linear to the number of cookie character sets, but with a smaller constant. Like this will be like, for example, you need on average maybe 64 requests on just 64, not 128 requests. And it's very fast, real fast. You see it in the demo because Speedy, thanks to Speedy really, because Speedy open the connection and reuse the connection. This doesn't need to open a new connection. It doesn't need to do the SSL handshake again, so it's super fast. That's why we didn't try to optimize because already too fast. And it's also false positive free. One of the difficulties is some of the servers, for example Twitter, they set a limit, like how many requests you can send to them per second, or maybe not per second, but concurrently. So sometimes if you send too many requests, they stop and Chrome will stone the connection, so you have to try again. The second kind of problem is different browsers actually have different implementation of Speedy header compression. This is one of the nice things about Deflate. Like, regardless of how you compress, the decompressor can still decompress. So different browser has different idea of how they want to compress things. So in order to have an exploit against Chrome and Firefox, you have to write different code. You cannot use the same code. Just a small modification, but still. Yeah. Okay. So one of the workaround is disable header compression in Speedy. Like they decide, oh, we just disable it. So it's now basically Speedy is beside the multiplexing all requests into set one connection. It doesn't have header connection anymore. But Speedy form may like they will compress again, and they have some kind of like tricks to prevent crime. Yeah. So this is for speedy. So, and I promised that to discuss something that doesn't require any kind of understand about compression and this thing. So, so the next thing we will discuss is compression in TOS. So this is kind of a history of compression in TOS. It's kind of weird. Like when they defined SSL in 1995, they said, oh, you can negotiate compression, but they don't actually specify any kind of standard, no kind of algorithm, so nobody implement anything until 2004. So in 2004, somebody like specify difflay, how you use difflay to compress TOS. This is the compression inside the transport layer itself, not in the application layer. Like the SL layer will do the compression, not like Speedy. Speedy does the compression and send to TOS. So maybe some people can do multiple compression, but it doesn't make sense because, yes, it doesn't make sense to do multiple layer of compression. So either you use this, or use Speedy, or use HTTP GZIP. So Chrome, no. Chrome, OpenSL, GNU TOS, they implement difflay. I don't know if there is anybody implement LZS. So one of the weird things about OpenSL compression in TOS is, so this is another boundary. So if the data is larger than the maximum record size, the record size is 16 kilobyte, TOS will split it into different record, 16K, 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 then compress each record independently without using a shared compressor context. So this is a nice thing. And when you think about it, it makes sense because basically SL. So when we discover this, we think it's kind of weird because the right thing maybe you compress the data, all of your data, and then you send it to TOS because it doesn't make sense to split it and then compress like independently. But if I think about it a little bit, and I think it makes sense because TOS actually operates on a record layer, so it doesn't know anything about the application data, so it can't like decide, oh, I compress this thing like together. It needs to make sure that when it decompress the bucket, the record, the decompressed record much less than the size of that decompressed record, much less than 16K. So that's why it split before it compressed. Okay. So the attack that the next attack that we call is 16K, 16 kilobyte minus 1. So 16K is essentially another boundary. And you will see that pitch fusion boundary attack will strike again, like it will apply here again. That's why I set up, this is one of the most important idea. So the idea is we make a request so big. Chrome and WebKit and Firefox allow you to do this, make a request very big. So that it will be split into 2 records. The first record will be like contain a long padding so that the first byte, listen carefully, the first byte of the cookie becomes the last byte of the first record. So S is the cookie, right? We have tweet ID equal to 0. And we design a padding because we know everything in the request except the cookie. So we design everything to make sure that the first byte of the cookie becomes the last byte of the record, and the second record be the rest of the request. Yeah. So this is basically the idea. So we split it into record, and the target is the S. We want to obtain S, right? Right. And if you look at this, you will see that what you see when you make a request like this. The length of the first record, right? You will see the length of the first. You know the compression algorithm they use. you know the length, you know the compression algorithm, you know everything but the last byte. So basically what you do is you can just turn to offline computation, you compress yourself. You know everything beside the last byte, you get that, concatenate with each byte in the cookie character set, compress them, compare with the length that you got from the network. If they are equal, you know that byte likely to be the correct byte, right? This is, maybe we have, back, yeah. So this is basically the idea. So you see, URL, we generate a random 16K URL. And then we query will ask the browser to send the request and obtain return the record length. And then we get the length of the first record. And then we do the compression. What? I thought that was someone from Twitter. So, where are we? Okay, compression, probably. Okay. So basically, this is a very cool idea. You don't need to know anything about compression. You just basically look at the network, get the length, and do the compression yourself. You can see records is URL is the URL you generate. REQ is the known headers, and known is what you have already knows in the cookies. And you will see here, it will compress locally, record plus C. C is one of the candidates, maybe A, B, C, D, E, F, G, H. And then if the compression length is different from length, then sorry, the course is wrong. Should be equal. So they will append good, C to good, and then after the loop, they will reassign candidates to good. And you see that it has a bigger loop outside to make sure that when it finished, you got the right character. So like you send a request, then get the length and do the compression locally to know which byte is maybe the correct byte. On the first time, you won't get the correct bytes because a lot of C will compress to that particular length. So you have to try again. Like basically you have to, okay, another request, try again with this set of candidates, and then until you get the only candidates. And we said that we have the best algorithms is just 6 requests per byte. That's algorithms. Because basically we can design the random 16K URL so that it split the candidates into 2 halves on every request. It split it into 2 halves. So for each request, you eliminate half of the candidates. So basically you can, if the list of candidates is 64 characters, like base 64, then on average, 6 requests, which is logarithm 64, you will basically, this is like a binary search to find the correct request, the correct byte. And this also works with AES. And the idea is you can design the URL so that the compression of record will be very near the boundary, the block size boundary. For example, it will be 15 modular 16, like it will be like 31 bytes, or maybe it is like 15 bytes. So that is very near the boundary. When you add a small change to the request, which is C, then it may fool the whole block, and AES and CBC will add a dummy batting block for you, so that you can basically have an attack against AES and RC4. RC4 is easier because there is no padding, so you don't need to do any kind of this thing. And in the demo that we post on the internet maybe last week, we also saw that it's work against Dropbox, and Dropbox use AES, not RC4. And you can see that this doesn't require any kind of knowledge of compression, even if they change the compression algorithm. Maybe next slide. So what I just say, it's required just log W, not linear, but logarithm, which is much better. And that we can choose between longer offline compression. Like if you're willing to send more requests, then you can turn the algorithm to make sure that, I want to send more requests. Or if you have more power, more computing power, you can choose to, I want to compress more. And the more you compress, you can maybe make sure that the number of requests you need is just like 4 or 5 requests. And it's false positive free because you always get the correct byte, you see, because you have a test. The test only return true if you have the correct byte. So you never got the false positive, you never got the incorrect cookie. And it doesn't depend on the algorithm that they use. Maybe somebody switch to LGS and it still works. And this has some problem. The first problem is Chrome was the only browser that supported TLS compressions. And because you rely on the ability to do the compression on your machine, on the target, on the attacker machine. So your zlib version must be the same version as the victim. But this is easy. You can do you can send a few requests to detect the version of zlib, because basically public version of zlib just maybe 2 versions. 1.1.2.3 or 1.2.5. So you have basically two choices, and you can send a few requests to determine which kind of library the victim is using, and you choose the correct one on your side. Okay, so how do you prevent this? So basically, so basically they disable compression. And Chrome is the only browser so far support compressions, and now it's disable compression. So I think basically TLS compression will be gone. Maybe not, but we have the next slide. We'll discuss why. But yeah. So, okay, the next thing we discuss is HTTP response GZIP compressions. This is probably the most popular compression on the internet, because basically I think virtually every website supports this thing. So they compress the response, transfer it over TLS. So basically you have the same problem again. Compression, then encryption, and leak the length. So, and basically they use GZIP, which is just a wrapper, like a layer. They have a few headers, a few bytes, a checksum, and a dictionary or something. Yeah. So this deflate on the way down. So, okay. And the idea for this attack is, so it has a new requirement. That's why we didn't develop like a demo for it, because it's application dependent. We need to find an application that has this requirement, that the server must echoes some input in the response, like, because basically the attacker must have the ability to inject something into the compression, right? If you can't control anything in the compression, you can't do anything. So you need the server to return something for you. And basically I think most applications have something like this, right? But basically you need something that the response is very static, like the response doesn't change much on several requests, so that you can do the compression, or you can make sure that no random thing appear in the compression, the response. And the target is what do you get from the response? Maybe you get the personal information like email address or friend list or things like that, or credit card. Or you can target something even better, is the roadside scripting request forgery token. Most of the response will have one token like that in the response, right? And if you got, so this idea, 2 tries, the first attack that we described may work. I don't think Speedy may work because probably GZIP doesn't use share compression context. And the attack sitting K-1 doesn't work either, because probably GZIP compress thing before it's sent to TLS. There is nothing like split then compress. They will probably compress then send it out to TLS. So maybe 2 tries may work. We haven't tried, so maybe we go to the next slide and then demo at the end of the talk. Okay, so we have some kind of short-term solution like disable compression, which is probably not something we want to use, right? So one other thing is maybe we replace cookie with something else. So there is some project which is something like they buy the cookie to the client certificate. Like they define some mechanism so that when you send some when you authenticate with some web server, the browser will generate a self-signed certificate, and that self-signed certificate will be used to share or something, do something with the cookie. So that if you steal the cookie from the victim, you can't use it because you don't have the client certificate. That's one of the ideas to harden the cookie system. But I think maybe we need something completely new. Like, because the way the browser does with cookies is kind of weird. Like, it's willing to give the cookies, which is something very important to every website in the world who asks us to, attach this to your cookie and compress them, do some transformation, and then send it over. It's willing to do that, and maybe we need something else that like completely replace cookie. And another idea is to fix the thing in the TLS protocol layer, like to hide the length, because I don't know if you are aware of this, but traffic analysis is already a big problem in TLS. Some people has did some very nice research in which they look at your network traffic when you declare your tax and they know your income. So it's already a big problem, and somebody are working on to fix this problem in TLS by using the approach like they split the request into randomly split it and randomly pad it. It won't stop gram, but it may slow it down to a arbitrary speed that it doesn't matter. Like it isn't interesting anymore. But the approach they are working on only apply for CPC. The problem is in the TLS standard, it doesn't have any kind of padding if you use stream cipher. And stream cipher is used everywhere in the world, like Twitter, Google, most of the biggest websites in the world, they use RC4 because it has better performance. And so probably we need a new version of TLS or some extension to make sure that we use explicit like random splitting and padding for on-cipher source, like regardless of RC4 or AES, probably requires some kind of RFC. But the fundamental problem is, like the fundamental questions is how to combine compression and encryption together securely. So I just see this on Twitter this morning, and actually I know Dan Bonet, and I discussed this attack with him, and he said, "Oh, this is very interesting. Like we will do this all the time. They combine compression with encryption, but there is no kind of work in crypto that actually to define a scheme or something that allow people to actually do compress and encryption, combine them together securely, like authentication and encryption. Like now we know we should do encrypt then MAC, but for compression, encrypt then compression doesn't make sense because when you encrypt, you basically turn your data into random, and if you compress the random, it doesn't make sense. And the more that people use usually is before gram is compress then encrypt, and now gram so that it doesn't make sense to do that either. So maybe we need something else, completely new. Yeah. Okay, next. Okay. So this is something that we haven't worked on, but we think this is like kind of prediction or maybe speculation. I don't like this, but I think maybe it's a good idea to solve so that somebody can work on it. So browser are not. So I said in the last slide that TLS compression has died, but actually no. We have a lot of other clients. Browser are not the only TLS client. There are all the protocols that use TLS compression properly. And the second thing, I think the second point is very important. And right now nobody is working on fixing it or maybe demonstrate a practical attack against it. Maybe next year at Ekoparty somebody will do that. So we have GZIP. I think this is a bigger problem maybe than both Speedy and TLS because I told him as I say, virtually every website support this. And virtually when the world move to HTTPS only, this thing will be affect a lot of applications. And if you think about it, you will see that when you get the XSR token and you control the network, you can basically take over the user account very easily. You can inject some JavaScript into some HTTP response and you send a request yourself. So the XSR token is most of the time is better than a session cookie because it won't be changed for maybe 2 weeks or 3 weeks. So and another thing is, as we say, compression is everywhere. So this is open resource area that I think very cool to work on. and I think all of us here are welcome to work on it to improve maybe or to break the security of the internet. Okay, the last slide. Okay, thank you to I'm here and Julio. Actually, personally, I'm here because Google support me. Google support my work and they pay everything and they're very nice. So thank you. And yeah. They even pay Juliano because it doesn't actually directly affect Google products. Maybe, yeah, it's affect, but like, but not directly. But they say, oh, this is so interesting, so they decide, oh, they have Pauti program, and they decide to reward Juliano something. And Mozilla, they're also very cool. Dropbox, so this kind of like Dropbox is kind of a new company, and I think they are extremely cool. Like we report the things to them, and they're very cool. So yeah, and lots of friends. We have Julino and I have lots of friends, and they help us review the things, to review the slide, to discuss, to support us. Thank you, and of course, Ekoparty. Thank you. The last thing I want to say is no. I don't know where my wife is. She's in church, like right before the top, like she stripped off the stair. I don't know where she is now. Yeah, so just want to say thank you her for coming here with me. Thank you. Okay. Maybe we do demo. Okay, we can do the demo. Any questions before the demo? I hope the slides are clear. Okay. Okay. Huh? Hang up? Yep, it's working. Oh, they can't hear me. Sure. Okay. We are looking for a TLS compression server, but we try to find something more interesting, like Yahoo Mail, but Yahoo Mail is so nobody uses it anymore, so we don't give another demo against Yahoo Mail. So we will give another demo against Twitter. We'll see the live one. So it's probably more interesting because things may fail, and I can explain why things fail, what we try to fix them. So Twitter. Okay, I will try to register. Okay. Yeah, they have this kind of losing flow. Okay. No. Okay. So we assigned to Twitter. And now I will start my proxy. Oh. So the code name for the project is Bees with Z. Okay, we start proxy and now we switch the browser to the proxy. So you can basically, if somebody is doing like transparent proxy, they can just like configure the browser to redirect to some transparent proxy. Yeah, because I try to do that, but because on Mac they don't have a good software to do transparent proxy, so I just use a explicit proxy. So this is not compressed, but you see the icon here to see an add-on to see that Speedy is enabled on this website. So we need to check the version of Chrome because Chrome is very smart. It's auto-update every time. I have to download the software locally to make sure that when it updates, I replace it with a vulnerable version. So yeah, if I relaunch it, it will finish the updating and fix the vulnerability. So now maybe we go to Slashdot. So when you go to Slashdot, you see the dot here because I insert an iframe, which is lamb, but it's just a demo, so I don't want to do something more complicated than it. You see something here, right? An iframe to twitter.com/gram. You won't find it on Twitter. It's just a mechanism so that I can basically to delete some unnecessary cookies that I don't want to get, and yeah, just basically that. So you see here, if we try to get a cookie, so it won't be successful on first few try, like because I haven't tried much to. So you look at here, you see like tweet ID u %3DA, and we can look at the cookie here to see if we have the correct things. You can see it's like first few is good now. Yeah. So it may take like, I think maybe a few minutes, maybe 3 minutes. So you see now, it's wrong. Like it get the wrong byte, but like as I say, it will detect, oh, it's got the wrong byte, it will try again and remove the wrong byte with the correct one. I hope so. Okay, so you see it's removed on the wrong byte now. It get back to 3D, just 3D. Yeah, it's got a little bit more time to get the right one. When it got the right one, it's very fast. Come on. So this is exactly what I just recorded yesterday. Just so you see, like we have a sniffer here. We sniff. So we have like you see here, land 1015. This is the first request we send to reset the dictionary, and then we send several requests to. You see, the second request is just 68 bytes. That's because the second request is very well compressed. So it's very well. You see, it's like 20-fold like degrees in size. Let's take a look. Oh, it's still here. Not very good. Yeah, just be more patient. So I can show something else too. Okay, Speedy. Yeah, so you can look at maybe a little bit about the JavaScript. This is the JavaScript I saw before. We will publish the code maybe in a few weeks. And this is the algorithm that we do. You see, we obtain the records, and then get candidates. We select the records, and you can see that the algorithm is basically what I saw previously. Like just select those that smaller than length. Length is the base length of the incorrect guess, and append good to append those things to good, and then here we assign good to cell candidates, and yeah, basically that's it. Where are we? Oh, better now. Yeah, we got something now. Oh no. So it's kind of stupid, right? Because
it doesn't know that when it's got the right one. Maybe it's eliminate, like it's got the right one and then it's got just wrong, one byte wrong, and then it's just remove all the right one. Oh, now it's good. You see, now 383872. Oh no, it's removed again. So maybe we'll try again. I don't know. Just wait a little bit more. I think it's will work. Last night I tried like I wait like 3 minutes and it works. Like just keep it like doing again and again and again. Now, so we need to look at the cookie. Maybe something's wrong here. Okay, should be easy. Yeah. Something's wrong. Okay, I will try again one more time. Sorry. I will. Maybe they have some like because I haven't like I wrote this like very quickly last night, so maybe there is something that I mistook. I will try again. Xảo. We are not a cow. Okay. I don't remember the last one. Password. Gmail.com. Okay. Okay. Sorry. This is this is boring. Sorry. Okay. I hope this time it's work. Okay. We are here. Okay, we switch to the proxy. Okay, let's start. Yeah. Come on. So I don't know why the first few bytes is always very difficult. I haven't like take a look very careful look to see why the first few bytes it's always have troubles in trying to decrypt the first few bytes. Yeah, maybe they fix it. No, I don't think so. Maybe we tried the other cookie first to see. Yeah. So the other cookie is all token. Okay. How is it this time? We need more patience, actually. Yeah, it's better. I think it's better. You see that now it's the token here, 328EA92. Let's take a look at here. Yes, it's better. I don't know. Yeah. So we got we need to get two cookies. The first is all token, and the second one is tweet ID. Is it bad? Yeah, it's nice. So it just keep trying something here, so one of the problem here is I told you because zlib contain a lot of optimization, so sometimes it interfere with the attack. When I design this, I I didn't try Twitter because I had some problem with Twitter because the server limit. So I tried with some other server and it worked very well. And until we got here, we start working on Twitter. So let's see, we got A6 here. This is the buy that we got from the drifter, and this is our token. You can see that the first few bytes is the same way. It just needs maybe a few more. Maybe we just need to wait a little bit. We try. So it's got 5 and then it's back up. Oh, now it's got interesting now. Oh, cool. Oh. Yeah, so it's good now. So we got the first cookie now. Yeah, we just need to be more patient. So this is the first cookie. I will compare with the thing we got. You see, it's exactly the same. Thank you. I'm feeling lucky now. So this second cookie is more tricky. Yeah, so I think we just need to wait a little bit more. Yeah, it will work eventually. Maybe until tomorrow, probably. So yeah, come on, yeah, nice. So it's. Maybe Julio can sing something. So with just the all token, we can't do anything. We can't sign into Twitter. We need the other cookie. Yeah, maybe it's shy because so many people are looking at it right now. So.
En realidad hasta ayer esto no andaba. Y estuvo cambiando cosas hace poco y debe haber cambiado algo muy tonto que no vamos a encontrar nunca ahora, pero después seguro es algo que se puede arreglar muy fácil. Pero básicamente la desencripción funciona porque funcionó con la otra cookie. Lo más probable que esté pasando ahora es que falte una de las letras o de los bytes que tiene que probar, que no esté en la lista de bytes que está intentando. O alguna optimización que se pueden agregar, que es cuando ya sabes que desencriptaste hasta ese momento. Él tenía ahí unos if por ahí que trataban de cambiar la cantidad de candidatos. Tal vez puede ser ese el problema. Pero no sé. Y
So this is the 16K debug script that I wrote to demonstrate the idea that we can change the parameter to make sure that how long we need to compress thing, and so here you see 5 is big, so it will compress, spend less time compressing, but send more requests. I modified this script to support like AES, and I will switch to RC4 again to demonstrate the idea. Yeah, still there.
Y ahora está haciendo un truco de magia, cada vez que abre el Python en realidad le está pasando el cookie al otro. No sé por qué no lo hace con la otra. No, mentira.
So you see, it's oh no, this is something else. I know because I was working on it. Sorry. Let's see. Okay. Random breaker.
¿Nadie tiene preguntas?
Yeah.
¿Se entendió todo entonces?
I forgot how I changed this. Maybe we said something else, huh? Oh, still no buy. I don't know why. Come on.
¿Cómo elige entre los candidatos? ¿Cuál elige? Depende en qué posición.
Maybe we can turn to question and answer.
Yes, I am.
We wait for this thing. As a success.
Empieza cuando sabes que con qué sitio, acá la demo está preparada para Twitter, entonces sabemos cuáles son las cookies. Además, y qué nombres tienen, entonces vos podés saber que si es exa, la cookie es solo exa, podés solamente probar cosas exa. Además, él cuando mostró algo que tal vez es confuso, que mostró que en Slashdot agregaba twitter.com/crime. Eso parece que tiene que ver con que es del mismo dominio. En parte sí, en este caso lo usa para obtener otras cookies que no son importantes, pero que son parte del pedido, para no necesitar desencriptar esas. Pero las que son seguras no las puedes obtener así, las que son HTTP only. Pero la pregunta es exactamente en qué candidatos elige. No prueba a todos. Después de cada prueba. Y eso habría que ver. Eso no sé qué hizo. No sé qué cambió. Pero en realidad lo que cambia al azar es otro pedazo del nombre del archivo. Eso va cambiando al azar. Porque al cambiar esa parte, cambian las frecuencias de los literales. Entonces van a cambiar las longitudes. Y cosas que se comprimieron de la misma manera en una prueba, en otra, como cambia la frecuencia de todo, se va a comprimir a otra longitud, van a cambiar las longitudes de todo. Sí. Claro, la pregunta es ¿qué pasa cuando dentro de las cookies se repiten cosas? ¿Eso es? Bueno, en este caso no importa. En el primero que presentó importaba, porque ahí se usaban las referencias. En este lo que está haciendo es, creo, es hacer que en cada paquete que se comprime haya 16K. Do you know? They want to know what you are doing and I don't know.
What? Yeah? Okay. So this is the script that I wrote to test the idea how you use the 16K-1 the tag again AES. So we have AES here. So one of the thing we must to do is to make sure that you generate something that compressed to a specific length, and it's not like very difficult. You can see what I do here is, so when I compress so this is the function to generate a random record, and when I generate it, I compress it, and I see the length. If the length is in the boundary of the block size, which is 16 bytes, right? So if it is not in the boundary, I just concatenate append a random byte, and eventually you will get a length that is like very near the boundary of AES. That's the basic idea. Another idea is how to decrease the number of requests. So basically what I do is, so compressed length will contain, dictionary contain the mapping between each candidate with its compressed length. And what we have here is, I just basically look over the candidates and compress each byte in the candidate, put them into the dictionary compressed length, and I make sure that the compressed length dictionary is balanced. Balanced means that it's split into two halves, which is more or less equal to each other. So that's the binary sort idea that I presented. Like, so I like that because I want that because when I look at the length, it's have to eliminate half or most of the candidates. So you can see what I do here. I compress and get the length, and then I see if the length of compression and the length candidates minus 2, which is divided to which is this statement makes sure that my compressed length is not very far away from the half, like it doesn't contain too many elements more than half the candidates. Like for example, if the candidate is 32 or 64, then it should contain like at most 37 like bytes, so that when I finish this, I send a request and obtain the length. I look up in the compressed length dictionary and I can eliminate half of the candidates. So that's like 2 ideas. And you can take a look at the speed area. Let me check this for one moment. Oh, cool, we have something now. I didn't type anything, you see, just to make sure. Okay, we got bus, like the tricky part, and I think it's will be finished soon. So we this is the thing that the algorithm that I told, the speedy algorithm. So I send like you see the first 2 requests. You see the comments. The first 2 requests are used to reset the state, the dictionary of the compressor on the browser, because we know that if we send requests like very near one after the another, then the compression context will be known. Like we know the compression context, and we send like 2 requests. Then for each C in the list of the candidates, we just like create an image. Like we send a JavaScript code to this gram.html, and it will just create an image. And the image will basically contain like the path where contain the path of the image, and the path is, if you look at it, you will see it's the S and yes. S is some padding. I have like 3 byte padding. You see a lot of tricks, like because I need to make sure that like zlib doesn't interfere with my like yes, because sometimes zlib will do some weird things, so I need to do that. 5 minutes? Okay. Oh, it's got back to the beginning now. Sorry. So maybe we don't have enough time for this. Sorry. But we will publish the code and you can reproduce the thing at home. So yeah, maybe I just leave the computer here and we run. Eventually we will have something. Okay, thank you. Any more questions? I will upload it in maybe Twitter. No, GitHub probably. And the slide will be uploaded to Netifera. So yeah, that's it. Thank you. Sorry, we just got the first cookie, not the second one. Too bad you didn't. Okay, cool. Thank you.
Vamos, un aplauso más fuerte a los chicos.